Assalamu alaikum, dear student. This is lecture number 2 of week number 6, and we are studying fluid dynamics. The topics we are going to cover today in this lecture are the flow measurement numericals for a closed channel such as pipes and conduits. The theoretical part we have already covered in the previous lecture, and now how to measure the flow in the open channel device, and we will perform a numerical for the open channel device, and finally we will perform and describe what is energy and hydraulic grade lines. So let's start the numerical which is related to the conduit or closed channel. This is the example 3.11 of your book. So here given kerosene has a specific gravity of 0.85, flows through the Venturi meter shown in figure with flow meter between 0.005 and 0.050 meter cube per second. So this is the question, this is the figure which is given. So what we have to determine the range in pressure difference P1 minus P2 needed to measure these flow rates. So there are two flow rates are given, okay, and we have to find out the range of pressure to achieve these flow rates, okay. So this is a Venturi meter, and this is the pressure difference gauge which is installed in the one limb in the higher the greater cross section area and one in the smaller cross section area, okay. So now we have to calculate the pressure difference. So we know the equation that we have derived previously for the flow rate. If you remember, the Q is equals to under root P1 minus P2 into 2A square under root rho 1 minus A2 over A1 square. So now if you have to find out the P1 minus P2, then take all the values to the other side, then P1 minus P2 will be equal to this factor, okay. So here you see, to find out the pressure P1 minus P2, what exactly the data we needed, okay. So here you see the Q flow rate is given, okay. Density of the kerosene, because the flowing liquid is kerosene, which is given. Area of cross section for the larger area is given, and area of cross section for the smaller dia is given. The diameter for the larger cross section and the smaller cross section is given, okay. So now everything is known. We can easily find out the pressure difference, okay, for this flow rate and for this flow rate. So now the specific gravity of the kerosene is given, but we need the density of the kerosene oil, which is very easy to find out, because the specific gravity is the ratio of the density of fluid divided by the density of water. So here it is. So we find out the density of kerosene, so which is 850 kilogram per meter cube, okay. So now we have to find out A2 minus A1. So A2 minus A1 is equals to pi D2 square, pi D2 square divided by pi D1 square by 4. So they're going to be cancelled each other, only D2 by D1 will be remain. So which will be equal to 0.36. Now substitute this value, okay. Now the pressure difference for the smaller flow rate, okay. Now we are going to calculate the pressure difference for the smaller flow rate, for the 0.005 for the smaller flow rate. So when we inserted all the values with the smaller flow rate, so we end up with the pressure difference which is 1.16 kilopascal, okay. So in the same way we are going to find out the pressure for the higher flow rate, that is 0.05 meter cube per second. So we inserted all the values including the flow rate 0.05 meter cube, which is given here, okay. So finally we got the pressure difference, that is 116 kilopascal, okay. So here what is the pressure range to calculate the flow rate range? So that is the pressure difference should be greater, should be less than 116 kilopascal and should be greater than 1.16 kilopascal. Okay, because the flow rate will come within this range. So this is for the minimum flow rate and this is for the maximum flow rate. So the flow rate other than these two value within this, so the pressure difference must be within this value. Okay, so here we can read out the comments little bit and we will see what is the outcome of doing this exercise. These values represents the pressure difference for in-viscid steady incompressible condition. For the ideal results represent here are independent of the particular flow meter geometry, an orifice, nozzle or venturi meter and this. So here it is very important point, okay, because you see we all know that there is a difference between the venturi, the nozzle and the orifice, because their geometries are different. But here, since we are considering a ideal condition, in the ideal condition we are ignoring all the losses, okay, including the geometry loss. If the geometry will change, what will happen? The losses will increase. That we have seen in the open jet flow. Okay, in the open jet condition we study the different orifice and types and the outlet of the orifice. Okay, if it is sharp edges, if it is smooth edges, then what is the correction factor? So but here, since we are considering the ideal condition, so no correction factor we are considering. So regardless the flow measuring device is orifice, nozzle or venturi, the reading will be same. Okay, but if because we are considering the ideal condition, because the no losses is considering, but when you consider the correction factors, the losses, the flow will not be ideal anymore. Okay, so here except the other losses including in-viscid incompressible condition, we are also not considering the geometrical losses or geometrical correction factor. Okay, so if you are going to use the geometrical correction factor, so the flow will be actual. Okay, so we will discuss on it little bit later. So let's see what else are the outcome of this problem. It is seen from equation 3.20. Okay, that this is the equation 3.20. Okay, that the flow rate varies at the square root of the pressure difference. Okay, so if you separate the flow rate with this, so what will happen? Because there is a square root, the square root will come over P1 minus P2. Okay, so here it's saying, okay, the flow rate varies as the square root of pressure difference. Yani flow rate is the function of square root of pressure difference. Okay, hence indicated by the numerical results as shown in figure 3.22, 3.11b. so this is 3.11b. you can see the flow rate is increasing as the pressure difference is increasing. Okay, you see the flow rate is increasing with the line as the pressure difference is increasing. In equation in the diagram E311b, 10-fold in case of flow rate requires as 100-fold increases in pressure difference. Okay, because here you see if the flow rate is increasing 10 times from here to here, the pressure is increasing 100 times from here to here. So what is the shortcoming because of that? This non-linear relationship can cause difficulties when measuring flow rates over a wide range of values. Okay, because the difference of pressure and the flow rate is very big. So if you measure the flow rate, okay, by using the same technique, then what will happen? There might be a big error in that. Because of that, what we should do? Such measurement would require pressure transducer with a wide range of operation. So we need a very sensitive pressure transducer that could measure, or as an alternative is to use two flow meters in parallel, one for the large and one for the smaller flow ranges, because there is a big range of flow rate, so that we have to take two alternative, either to use a very precise and long range transducers. We know that the transducers are very sensitive to measure the pressure difference, or we have to use two different flow meters, one for the smaller flow rate and one for the large flow rate. Okay, but here you see in this example, these equation for the ideal fluid flow, the flow rate what we are measuring from this equation, this is for the ideal flow rate. But here, thus as shown by the figure A, so this is the figure A. Okay, in the margin, for a given flow geometry A1 and A2, whatever is the A1 inlet and whatever is the outlet, the flow rate can be determined if the pressure difference P1 and P2 is measured. Okay, if you know the pressure difference, you can easily find out the flow rate by using this equation. Okay, this is the equation 3.20. Okay, the actual measure flow rate will be smaller than this theoretical result, because this flow rate we are measuring without any losses, so definitely the value of this flow rate will be greater, but the actual flow rate will be smaller than this result what we are getting from this equation, because of the various differences between the real world and the assumptions used in the derivation. This is the theoretical flow rate. This equation will give us the theoretical flow rate of these differences, which are quite consistent and may be as smaller as 1 to 2% or as large as 40%. The value between the actual and theoretical might be this much, depending on the geometry used. Okay, if you are using a orifice gives you a large pressure drop. Okay, and the nozzle will give little bit less, and the venturi will give you a smaller pressure drop, because this is a smooth discharge. Since the actual discharge from the orifice can be measured like this. Okay, so what is C? C is the correction factor or the correction coefficient. Okay, so by using this equation, you can calculate the actual flow rate, and theoretical flow rate you can calculate from this, and C is the correction factor, the type of geometry you are using for it. Okay, so this is end of the flow rate measurement for the pipe and conduits for the closed channel. So now let's start the open channel flow measuring devices. The open channel flow measuring devices, what exactly it is? The flow meters based on the Bernoulli equation are used to measure flow rate in open channels such as flumes and irrigation ditches. Okay, flumes, you all know, that is basically you might have visited the water park. You might have seen the water tunnels through which the people slides and jump into the pond. Okay, so those pipes or tunnels through which we slide, that is called flumes. And irrigation ditches we will see here. So this is basically the irrigation ditches. Through here we serve water to the canals which serves throughout the field. Okay, and this is the construction, this is the flow, the way it flows through the gate, that is called sluice gate. Okay, this kind of construction is called sluice gate, and this is called the weir geometry. Okay, normally you will perform in your practical to calculate the flow rate by using weir in the open channel. Okay, so this is a weir and this is a sluice gate. Okay, so now let's see how do we measure the flow rate by using the open channel flow meters. Okay, so here we are using a sluice gate. So the flow Q is the function of the width, depth, upstream Z1. So this is the upstream, because as much as it is higher, okay, the flow rate will be higher. The flow rate is depending on Z1. The width of the gate B and the gate opening A, application of the Bernoulli equation. Okay, so the Q is depending on three factors: Z1, B and A. So this is height of the water. okay, that is Z1. A is the height of the opening, this is height of the opening from here to here, which is given, and B is the width of the opening or width of the gate. Okay, so if you apply the Bernoulli equation between point 1 and point 2, okay, so apply the Bernoulli equation between point 1 and point 2, so the Bernoulli equation will become like this. Okay, and at the same time we can apply the continuity equation. Okay, so whatever the amount of fluid will reduce here, the same amount of fluid will pass out from here. Okay, so we apply the Bernoulli equation in the form of we apply the continuity equation. So Q is equals to A1 V1. So Q is equals to A1 V1. What is A1? The area here and area here. So this is the velocity V1, and what is the area? What is the area here? B is the width. Okay, and that is H is the Z1 is the height. So V1 B Z1 is the area and V1 is the velocity at this side. So at 2, what is the area? At 2, the area we have A into B. So A, okay, A into or Z2. This is also called Z2. You can see here. Okay, this is Z2 because the area of the Z2 will be less than the area of A. Okay, so this is called vena contracta. You can see that. Okay, so this is B into Z2 into area V2. Okay, so now you apply. Now we have to find out the flow rate. So you can apply the value of V1 and V2 in this area. Okay, so here the atmospheric pressure, you know that is P1 is 0, and here also there is a open channel, so atmospheric pressure at 1 is 0 and atmospheric pressure at 2 is 0. So P1 and P2 will be 0. So V1 will be equal to some factor, separate V1 from here and separate V2 from here and insert the value in this equation. Or you can do also, you can put V1 is equals to in the form of Q. Okay, you separate V1 will be equals to Q over B over Z1, and V2 will be equal to V2 is equals to Q over B over Z2. So insert this V1 and V2 value in this equation and separate for Q1. So finally you end up with Z2 is equals to under root 2G Z1 minus Z2 under root 1 minus Z2 over Z1 square. So this will be the final flow rate equation for the open channel flow. Here Z1 is much greater than Z2. You can see here. Okay, so Z1 is very greater than Z2. So in that case we can neglect. Okay, we can neglect it. So Q will be equal to, because this is we ignored and Z2 we ignored, so this is going to be equal to 1. Okay, so this is going to be 0. So if we are considering it is 0, it is 0. So it will be, this will become 1 and this will become 2G Z1. So equation will become equal to this if we are considering Z1 is very bigger than the Z2. So this is a very simplified form, but even then if you want to consider Z2, you can use this equation. Okay, but this will not give you much effect on volume flow rate in the open channel if you ignore Z2. Okay, so let's do one example for the open channel. So here you can see water flows under the sluice gate shown in figure this. So determine the approximate flow rate per unit width of the channel. So we have to find out the per unit width of the channel. Okay, so let's see, it is given, you see this is your A and this is your B, the width is given. Okay, sorry, this is Z, this is Z1 up to here, this is your A and this is your Z2. Okay, because you see the height of this and the thickness of this is different. So this is your Z2 and this is your A and this is your B and this is your Z1. So you inserted all the values here. Okay, so finally Z1 is equals to 5. Okay, A is equals to 0.8 which is given, and A over Z1 is equals to 0.1 over 6 less than 2.0. Okay, so we can assume that the condition coefficient, see, actually you see here because you see this Cc is the geometrical correction factor, okay, between the vena. This is called the vena contracta because this is the area is less than the area of the area of the discharge or the thickness of the discharge. So what is the relationship between them? This is your Z2 and this is your A. Okay, so Cc is the ratio between Z2 over A is equals to 0.61. So by using this you can calculate Z2. So that's why we calculated Z2, and finally we inserted all the values here, and finally Q with respect to width we got 4.6 meter square per second. It should be meter cube per second because but per unit width we are calculating, so it will be 4.61 meter square per second. Here if we consider Z1 is greater than Z2, then neglect the kinetic energy of the upstream fluid we would have. Okay, so the value will be reduced to 4.83 meter square per second. So you can see the value is increased here a little bit. So in this case the difference in Q with or without including V1 is not too significant because the depth ratio is fairly large. Okay, because here we are not increasing the kinetic energy because the V1 we are neglecting. Okay, so because of that this part is increasing, but it is that increase not that much. Okay, so here neglect the kinetic upstream from the gate compared to the downstream of it. Okay, so by repeating the calculation for various flow depth Z1, the result shown in figure, these are obtained. Note that. Okay, so if Z1 is varying, okay, with the same outlet, so how the flow is increasing you can see in the graph. So here you can see the flow rate is not directly proportional to the flow depth. Okay, because the graph is not like this. Okay, it is not like this. So thus, for example, if during the flood condition the upstream depth doubled from Z1 5 meter to 10 meter, then what will happen? Because you see the Z1 we are increasing. Okay, so if you double the height, so what will happen? The flow will be double? No. So here you can see the flow rate per unit width of the channel would not be double, but would increase only from 4.6 meter square per second to 6.6 meter, almost 1.5 of the previous flow rate. Okay, it will increase only 1.5 time of the previous flow rate, so it will not double. So this is basically the understanding that we get from this equation. So this is the end of the open channel flow rate. Now let's start the third topic of today, that is energy and hydraulic grade lines. Now the energy grade lines, what exactly it is? So this is all about the Bernoulli equation. The Bernoulli equation represents the partitioning of energy for an inviscid, incompressible and steady flow. So basically the Bernoulli equation separates three types of energy. Okay, so here a useful interpretation of Bernoulli equation can be obtained through the concept of hydraulic grade lines and energy grade lines. So we will see how the energy grade line and the hydraulic grade line are useful and what exactly they are. So what is the outcome of these grade lines? These concepts provide the geometrical interpretation of a flow. It also helps to visualize how mechanical energy changes in a flow. Okay, so how it is, you can see, we can see here, this is the geometry of the pipe is changing from bigger to smaller. Okay, so this is basically the energy grade line. I will explain it to you further, but just explaining this line. And this is your hydraulic grade line, and this is your geometry. As the geometry is changing, you can see the hydraulic grade line is changing. Okay, so basically, and this is the different type of energies, mechanical energies, which is showing here. So how we interpret, how we understand and how we build these lines I will explain to you in later. So here this is the Bernoulli equation. So Bernoulli equation basically is the component of three different heads. So this is the static head, this is the static pressure head, this is the dynamic head, and this is the hydraulic head or potential head we say. Okay, so this is basically indicating the total head. Okay, the total head which is indicating with the H. Okay, because if you solve these three components you will end up with the unit of meter, because Z is the height in the meter, P over gamma is basically the meter, V square over 2G is the meter. So when you add them together you will get a unit of a height. So this will give you the total height or total H of the flow. Okay, so here each term of Bernoulli equation has unit of length and represents a certain type of head. So this is, as I explained to you earlier, this is static head, this is dynamic head, and this is hydraulic head. Okay, or this is pressure head, this is dynamic head, or this is hydraulic head. Okay, so the Bernoulli equation states that the sum of pressure head, the sum of pressure head, sum of velocity head, and the elevation head is constant along the streamline, because this is all equal to a constant. Okay, along a streamline, this constant is called the total head. Okay, so the total head during the flow it remain constant. Okay, this is the concept. So energy line is a line that represents the total head available to the fluid. So this line, okay, this line represents the total head. Okay, the energy, and this line is called the energy line. Okay, EL is energy line. So the energy line represents the total head. Okay, next, as shown in the figure, the elevation of the energy line can be obtained by measuring the stagnation pressure. Okay, stagnation pressure is basically the total pressure with the using of pitot tube. So this is, you see, the pitot tube. Okay, pitot tube here at the inlet, pitot tube here at the exit, and if you put some pitot tube in the middle you will get the same head. Okay, or same column of the fluid. So if you join all the line you will get the energy line. Okay, so the energy line can be used by using the pitot tube and in the sequence or in the series of the flow line. Okay, and here the attached piezometer. So you see, this is the piezometer. Okay, it is directly connected with the tube. The attached piezometer tube measures the sum of the static pressure head and the elevation head. Z plus P over gamma, this is the elevation head, and this is the static pressure head. This sum is often called the piezometric head or the hydraulic grade line. Okay, so when we join this the piezometric column height together, so this will give us the line that is called a hydraulic grade line. Okay, so here further, since the total head along a streamline remain constant, therefore the pitot tube measures the same total pressure at any other location in the flow. Okay, so however the elevation head, velocity head, and static pressure head may vary along the streamline. Okay, because these pressure may vary but the total head will remain constant. Okay, the locus of elevation provided by a series of pitot tube is termed as energy grade line. Okay, because the locus of the pitot tube, this is the locus of the pitot tube, this is the locus of the pitot tube. If you join them together, this is the locus of the pitot tube, this is the locus of the pitot tube. If you join them together you will get a energy grade line. Okay, and the locus of elevation provided by a series of pitot static tube or pitot static tube is termed as energy grade line. Okay, and the locus of a static pressure head provided by a series of a piezometric tube is termed as hydraulic grade line. Let's go back and see how they are. So you see, this is the piezometer. If you join them together, the locus of these piezometer, so you will get a hydraulic grade line. Okay, so here, under the assumption of Bernoulli equation, the energy line is horizontal, because we assume that in the Bernoulli equation the flow is incompressible. Okay, there is no loss in the energy. The flow is steady. The flow is incompressible. Flow is steady, and the flow is inviscid. Okay, so these are the assumptions. Based on that, the energy line is constant. So here you see the energy line is constant because of that assumptions. Okay, the energy will never lose. The energy at point 1 is same as energy at point 2, because P1 over P2 over P1, because in the Bernoulli equation, the energy at point 1 and energy at point 2, energy at point 3 is constant. Okay, if the flow is ideal, okay, if the flow is ideal, energy will never lose, it will remain constant. Okay, but if the fluid velocity changes along the streamline, the hydraulic grade line will not be horizontal. Okay, because if the fluid is moving at the initial stage, the hydraulic grade line and the energy grade line are same, because the velocity is 0 here. Okay, velocity is 0 here, so energy grade line and the hydraulic grade line are same. But as the velocity changes, you see, as the fluid enters to this pipe, the velocity changes. So here you can see, as the fluid enters to the pipe, definitely the velocity will change. As the velocity is changing, okay, the hydraulic grade line is coming down. Okay, the hydraulic grade line is coming down. Okay, the velocity, this is working like a nozzle. When it passes from, because it's converging, so when it passes from bigger area to the smaller area, the velocity further increases. Okay, so what happens, the energy grade line will come further down. Okay, and then when it comes out, so what happens, the hydraulic grade line, the hydraulic grade line is equal to the atmospheric pressure. Okay, so here this hydraulic grade line is the same as the atmospheric pressure. Okay, so this is how the hydraulic grade line varies, but in the ideal flow case, energy grade line remain constant. So here we can say that if the viscous effects are important, if you are considering the viscous effect, you are considering the losses, so what will happen in that case, the total head does not remain constant. Okay, the energy will lose, that means energy is losing. In that case, the energy grade line will not be constant. This will also change as it passes through the different type of geometry of the pipe. So when it will pass through the reducer, the pressure will drop. When it will pass through the expander, the pressure will increase, and accordingly the line will move ups and down. So here, if the viscous effects are important, then the total head does not remain constant. This line will not remain constant due to the loss of energy along the streamline. It means that the energy line is no longer horizontal line. Okay, so if you are considering losses, so energy line will not remain constant, it will change. Okay, as the hydraulic grade line is changing. Okay, so the hydraulic grade line is the sum of the elevation head plus the static head. Okay, so if the velocity is changing, the static head will reduce and the dynamic head will increase. When you come here, the velocity will increase, your static head will reduce. So here the static head is 0 because the static head is equal to the atmospheric pressure. The sum of the total energy head is the elevation head plus the dynamic head. Let's move to the further. The energy line and hydraulic line for flow from a large tank are shown in figure. Okay, that we have discussed already. If the flow is steady, incompressible and viscid, the energy line is horizontal, that we already discussed. Okay, and at the elevation of the liquid in the tank. Okay, So the hydraulic grade line lies a distance v square 2g below the energy line. So always the hydraulic grade line will be v square over 2g below the hydraulic grade line. So this is the difference between the energy grade line and the hydraulic grade line. Okay, so as the velocity will increase, the hydraulic grade line will decrease. As the velocity will decrease, the hydraulic grade line will increase. Okay, when the velocity is 0, then hydraulic grade line and the energy grade line will be on the will lie on the same line, as you can see on the top. Okay, so let's see. Therefore, a change in the fluid velocity due to change in pipe diameter results change in the elevation of the hydraulic grade lines, as shown in the figure that we have discussed. At the pipe outlet, at the pressure head is 0, so that the pipe elevation and the hydraulic grade line is coincide, that we have discussed in the previous diagram. If the pipe lies below the hydraulic grade line, so this is the pipe and this is the hydraulic grade line. If the pipe below the hydraulic grade line, the pressure within the pipe is positive. Okay, here the pressure is in the pipe is not here. If the pipe lies above the hydraulic grade line, if the pipe lies above the hydraulic grade line, the pressure within the pipe is negative. Okay, so thus a scale drawing of pipeline and hydraulic grade line can be used to indicate the positive and negative pressure region within the pipe. Okay, so here the quick review of the hydraulic and energy grade line. You can see what is hydraulic grade line is the sum of the static head and the elevation head. Energy grade line is the sum of static head, dynamic head and the elevation head. Dynamic head is equals to v square over 2g. So here you can see the hydraulic grade line HGL and the energy grade line is EGL for free discharge from a reservoir through a horizontal pipe with a diffuser. So basically this indicating for the actual flow when the flow is viscous. If in the case of viscous flow, you know that the hydraulic grade line will not be, the energy grade line will not be straight. Here you see the energy grade line is also going down. Okay, the straight line is energy grade line and the dotted lines is the hydraulic grade line. So here you see this is the large reservoir. In the large reservoir, when the fluid enters to the pipe, okay, so this is your static, this is piezometer and this is pitot tube. As it enters to the head, the velocity increases from 0 to some value. So as the velocity increases, the dynamic head appears and this is your elevation head, this is your static head. So static head decreases. Okay, so the difference is v square over tg, and since it's entered to the pipe, so there is some losses due to the contraction of the area. Okay, there is some losses here, so this energy line is not straight, it also reduces. When you see, this is the loss due to the area. Okay, so when you come here and again here you see this is the nozzle and it's expanding. Okay, the area is expanding, so the pressure is bit increasing. Okay, so here you can see the further this is the velocity change and this is again the pressure changes. Because of that it's going further down. Again you can see here the velocity is again some value. So here you can see because of this diffuser, okay, the pressure increases. You can see there is the pressure increases and there is little bit increase in the decrease in the velocity as well, because and also these are energy line is decreasing also because of that, because of the losses, because as the pipe is passing through the different fittings, the energy is losing continuously. Okay, then we pass to the straight pipe and further it is going down, and because of as it is passing through the pipe, because of the energy loss, these two lines are parallel. Okay, so here is basically this is indicating the energy grade line and hydraulic grade line for the actual flow. So let's summarize the notes for the hydraulic and energy grade line. Number one, for stationary bodies such as reservoirs or lakes, okay, if the fluid is stationary, or for the large reservoir, the energy grade line and hydraulic grade line coincides with the free surface of the liquid. Okay, so that I said that when velocity is 0, then energy grade line and hydraulic grade line will coincide with each other. The energy grade line is always distance v square over 2g above the hydraulic grade line. These two curves approaches each other as the velocity decreases, and they diverge as the velocity increases. So this is understood. Now in an idealized Bernoulli flow type, EGL is horizontal and its height remain constant. Okay, this is also understood. For open channel flow, the hydraulic grade line coincides with the free surface of the liquid, and the energy grade line is distance v square 2g above the free surface always. So next, at a pipe exit, the pressure head is 0 atmospheric pressure, and thus the HGL coincides with the pipe outlet. That also I have explained. Okay, the mechanical energy loss due to the friction effect conversion to the thermal energy cause the EGL and HGL to slope down in the direction of flow. The slope is measured of the head loss in the pipe. A component such as valve that generates significant friction effect causes a sudden drop in both EGL and HGL at the location in the actual flow. A steep jump drop occurs in EGL and HGL whenever mechanical energy is added or removed from the fluid. Like if you are adding pump or turbine, definitely the flow will jump. Okay, the gauge pressure of the fluid is 0 at location where the HGL intersects the fluid. Okay, so whenever the fluid is open to the atmosphere, the HGL intersects the atmosphere. The pressure is in a flow section that lies above HGL is negative, and the pressure in a section that lies above below HGL is positive. Okay, so this is end of the lecture.